Okay, so there's like a crazy amount of formulas on the board. And these formulas are used in different areas of math or science or research or study or statistics or whatever. But they're all actually quite similar. All right, so I'm not going to make you like memorize all these things. But if you look at them, there's a lot of similarities between them that I want you to realize. So first off, there's always something equals, piece of cake. And for most of them, notice that there's a number in front, and then there's like a base with an exponent. Number in front being multiplied with a base with an exponent. And check it out. Number in front, a base with an exponent. This stands for principal value. That's actually one thing. And then here's a base with an exponent. And same thing over here. A number in front and some base with an exponent. Those equations, aren't they all the same actually? Same kind. I know, you're like, no, those are ridiculous. Those are crazy different. They're similar, right? Can we agree on that? I'm going to make you shake your head. Yes, they are similar, just because I don't want you to be scared and complain 20 minutes from now where you're like, what? Because they're the same thing. Trust me, they're the same. All we have to figure out is, what do the different things mean? Well, remember the first one we worked with? Y equals AB to the x. Oh my gosh, that looks so familiar. And look at that. There's a number in front and then a base with an exponent. They're all of that form that we've been using, that we used on Friday. Do you remember what the number in front represented? A? What did that represent in like our word problem? Please, someone remember. Exponential growth and decay. A is the starting amount. You know, we have a test in 2 days, right? Maybe look up on some of that stuff. All right, starting amount. And every one of these other formulas where I've underlined like something in front, guess what that number in front represents? The starting amount. Yeah, they're just different letters to represent it. It's in different areas of business, they're called different things. Like in finance, it's called the principal value. It's the starting amount. And then there's a base to some exponent. A lot of them have t in them. What do you think t stands for? The time frame, right? How many times it's going to kick in and activate to grow exponentially or whatever. Yeah, timeout. So they're all pretty similar. R, we used R before, right? What does R represent? On Friday when we had our exponential growth or exponential decay problems, in the parentheses you had 1 plus R or 1 minus R. Do you remember what we plugged in place of that R? The percentage, the rate. R stands for rate. So if it's growing at 10%, R would be 0.1, right? You convert the percent to a decimal. Yeah, so they're all pretty similar. So let's just see how this works. We're going to talk about some investments today. I was talking to my boy Spider-Man, and he's actually opening up a bank account. He needs to save up some money to buy web fluid, and because Aunt May's birthday is coming up, and he wants to get her something special. And so he's got this savings account, and he's putting $1,000 in the savings account. It's getting 10% interest, and he wants to know once he finishes his education, how much money will be in the account in 12 years. He's got a 12-year school program in mind because he can only take one class at a time because he's out like saving lives, fighting crime all the time. So he's in like a 12-year school. They're rare. They're for superheroes, I've heard. Anyways, so how much money will he have in 12 years? Have you ever heard of investments or interest in a savings account? Is that something that you've heard at some point? You might not know exactly how it works or whatever, but it's something you should be familiar with. And interest is essentially money that you get for free from like the bank or wherever you're saving your money. It's almost like you're telling the bank, hey, Mr. Bank, take my money, take this $1,000 and hang on to it. And you can do whatever you want with it. You can let them spend it. But when I come back to get my money back, like in a year or 2 years or 15 years from now, it's going to be worth more than that. It's not going to be just $1,000. It might be like $2,000 or something because you earn interest. And interest is basically a fee that the bank was paying you as like a thank you for letting them borrow your money temporarily. Now, the reverse also works. If you were to make a large purchase in your life, like does anyone here ever plan on buying their own car or perhaps buying their own house at some point in their life? A majority of you probably will. But like a house can cost $150,000 or $500,000. It's a lot of money. Most people don't have like $150,000 just in their pocket that they can just take out of their wallet and be like, here you go, sir, I'd like to buy your house. That doesn't happen. So what people do is they go to a bank and they're like, hey, bank, I want to buy this house. I don't have that much money, but you do. You're a bank. You got tons and tons of money. Lots of people give you their money. Can you buy the house for me right now? And over the next 30 years, I'll pay you a little bit of money each month until I pay that off. The bank's like, sure, here's our money. We're going to buy the house for you. But as a thank you, then we have to pay interest to the bank. It's because the bank like put that money up front for us, and we're the ones living in the house. So we pay back that $150,000 plus some additional money every month called interest. And that's basically the fee for allowing for the bank allowing us to use their money to buy the house right away. So that's kind of what interest is. And so it's a good thing to get for yourself. It's free money. You're getting money just by letting your $1,000 just like sit in that bank account. It's growing. It's getting paid for doing nothing at all, which is pretty awesome. And so if we think about this, 10% interest, start with $1,000. So let's make a little table here. At year 0, we've got $1,000 in the bank. In 1 year, I'm going to gain 10% interest. That means I'm going to take 10% of that $1,000, which, what is that? What is 10% of 1,000? Does anybody know? It's $100, right? So I'm going to get $100 of interest after that first year. So now the total amount in my bank account is $1,100. I got $100 for free. I didn't do a thing. I just left that money alone, and now there's more. It's pretty cool. Now here's what's even better about interest, the way that it works. Now I let another year go by. I get 10% interest. Is that going to be $100 again? No. What's it going to be this time? It's going to be $110. Because there's a larger amount in that bank account, 10% of a bigger number is more money. So the next year, I actually get to make for free $110. Not just $100, I get $110 the next year, which is pretty groovy. So I have $1,210. A third year goes by, I get 10% of whatever's in there. So now I'm getting $121 for free. Look at that. In just 2 years, I've already made like $21 more per year than I did at the start. So each year, that interest percent is getting bigger and bigger and bigger. This is called exponential growth, right? When you're getting more and more and more each time. If I were only getting $100 every time, if I were to graph it, it'd just be like a straight line. I'm getting exactly like $100, $100, $100, $100. It'd be a constant slope. But because we're actually getting this interest and you're getting 10% of a bigger number every time, it's going to actually grow like this. It's going to be that exponential slope, which is good for us whenever it's our money getting interest. When you're paying off your loan to the bank, it's not that good because you're going to be paying a lot more money for that house than if you had all the money up front. All right, but if I asked you this, how much is in the account for 12 years? Do you think you could figure it out by doing it by hand like this, making a table? Could you do that 12 times, adding 10% every time? Are we all capable of doing that? Yeah, we are. Do you want to do it that way? Or do you want to find the quick and easy, fun mathematical formula shortcut way? Yeah, you want to use math, don't you? So we have a generic exponential formula. By the way, some of you might be thinking, Wojcik, there's not enough room on my slides for this notes. That's right, that's fine. I'm more so giving you those notes just so you have the word problems written out so you don't have to copy them down by hand. You might still want to probably have a separate notebook out for all your calculations and things like that. Might just make it easier for you. So Let's try figuring that out in terms of this equation right here. Or the one from Friday. Remember exponential growth and decay? So y equals, this is definitely growth because it's interest. A is our starting amount. It's $1,000. Times 1 plus the rate. What's the interest rate here? 0.1, right? It's that 10%, but converted to a decimal is 0.1. And then the exponent is just time. And it says they get 10% each year. I want to know after 12 years. So this is a problem that we did on Friday. You could easily type that in. Yes, we can grab calculators out if we don't have them yet. That's not something we're going to do in our head. Anybody else get 3,138? Nice. So I'm getting this 10% every year over 12 years, and I'm adding it to what was in there originally. Now that formula, though, is kind of cool. So if you break it down, it's like $1,000 plus 10%, which is 100, or times 0.1. Isn't that how we calculated our first year? We took 1,000 plus 10% of 1,000, right? That's the year one. Oops. So that's how we calculate the first year. I had $1,000 and I added 10% of $1,000. And if I look at this, there are two terms. That's super crooked though. Come on, Wojcik. Plus 1,000 times 0.1. If I look at those two terms, what do they both have in common? $1,000. See how they both have 1,000? Remember GCF, like factoring, how there's something in both terms you could like bring it out in front? Watch what this looks like. If I take 1,000 out of each of those, I'd be left with 1 plus 0.1. Does that look familiar to you? 1,000 times parentheses 1 plus 0.1. Look at this. 1,000 times 1 plus 0.1. That's how that formula was created. That's what it's derived from. And the exponent is just because you're going to repeat this over and over and over again. You're taking 10% of what you had the previous iteration. It's going to just keep on growing that way. Pretty cool, right? Yes. Now, today we're going to talk about something called compound interest. Yeah? Oh, sure. I can go over that real quick. Exponent button? It's the little caret. Looks like the roof of a house. Yep, hit that to do your exponent. You got it now? Okay, was everyone else able to calculate that? Before we move on, is there anyone who's like, I don't know how to, I can't find a button on the calculator or something like that? I'm happy to help you with that. So basically 1,000 parentheses 1 plus 0.1 close parentheses, and this is what we call the caret symbol. It's like the little roof of a house, I guess. To the 12th, hit enter, and you get that 3138. All right. Yeah. You don't see the symbol on yours? So then this one, it's going to be that button, the y to the x. So if I want to do 2 to the third, I would type 2 raised to the third, which is 8, right? 2 times 2 times 2. You're welcome. Anybody else? Calculator questions? It's definitely something you need to know how to do, and I'm happy to help you with your calculator. Oops, too much. Okay, so the new thing today that we're going to talk about is something called compound interest. And we kind of saw a little bit about that on that first problem with Spider-Man, where I was getting 10% interest, but after a year, I got interest on my interest, and that's what causes this exponential growth. And this formula right here is the key one to take into account whenever interest is paid multiple times per year. And so the one that we just did, Spider-Man's account gave 10% interest at the end of every year. But a lot of financial institutions or banks or whatever will pay you some of that interest a little bit each month. And so this is our compound interest formula. And I broke everything down for you. A lot of it is really similar. You already know terms like the final amount, right? That's usually the y. Y equals AB to the x. We've seen that before. P, that's just our starting amount. It's called the principal. That comes from the world of finance. They called like the initial investment the principal amount in there. And so that's just our starting value. So it's just a different letter, same idea that we've been using. R is the interest rate. That's just the percentage converted to a decimal, right? You just take that percent and divide it by 100 to get a decimal point. That's something that we also already did on Friday. T, down at the bottom, the time periods, that's also something we're familiar with, right? The exponent x was how many times does that kick in? And then the only other thing that we kind of need to look at is n. This is new. And it's the number of times that interest is applied. So a common term, I guess, within a bank or a savings account or a credit card is something called an APR. And that basically means how much percentage of interest you're going to get at the end of the year. But they might give you a fraction of that percentage throughout the year each month. And so that's kind of why in the warm-up, I had you look at terms like quarterly or monthly or daily. Because if you get interest compounded monthly, well, then that's going to actually change how often you get it. You're going to have to know, oh, well, then I'm going to get a fraction of that, a 12th of that interest each of the 12 months of the year. And that's what this formula does. So if you're getting interest that's compounding like monthly, then over the course of a year, you get that interest 12 times, once every month. And so if you look at this part right here, you take the rate and you divide it by the number of times interest is applied. So if I'm getting 12% interest over the course of a year, but it compounds or grows monthly, instead of getting 12% every month, I'm getting 1% every month. Because over the course of 12 months, it's going to add up to 12 ultimately. And so you have to divide the rate by the number of time periods, or in this case, divided it by 12 months. You're getting 1/12 of that each month. At the end of the year, you've got the full year's worth of interest. But then since you're getting interest monthly, you then have to multiply those 12 months times the time frame. So if it's after 2 years, but you're getting interest monthly, that's actually 24 months. You take those 12 months times 2, times the 2 years that you're checking it to get 24. So that's going to be the only new application piece really that we're looking at today. So go back to that Spider-Man example. And I want you to label each of these pieces of it, each of these letters in that new formula. A, P, R, N, and T from the Spider-Man example. So look at that table that I gave you, just to the right of example 1, where you've got that Spider-Man investment problem. And identify each of these. So what was A? And then what number would you give A in that problem? What was P? So you look at the chart. Oh, what does P represent? And look for what P is here and write it down in that table. So just make sure, can we identify each of these pieces? So not just like what they represent. I gave you all that right here. I want you to use this problem to actually identify the number for each of those based on the word problem. Good, very good. Okay, so A, remember in this formula, this capital A represents that final amount. What was the final amount for Spider-Man's account? That was like 3138.42, 43. Awesome. Okay, that was the end result. P, that stands for the principal balance or the starting amount. How much did Spider-Man invest originally? Just $1,000. R is the rate. That's not the percentage. You take the percentage and you convert it to a decimal simply by dividing it by 100, because 100 is the maximum percentage of something you can have. And so we want to take that 10% and convert it to a decimal, 0.1 or 0.110 if you want to keep that in there to remind you that's 10. Doesn't make a difference. That's the rate. Down at the bottom, I'm going to skip N for now. T was 12, right? It was 12 years. But what should N be? N is the number of times interest is applied. So to figure out N, you need to look in the word problem right around the percentage, wherever it gives you that percent sign. So here, it earns 10% interest, and typically right after that, it'll tell you how often. How often does Spider-Man get that 10% interest? Each year. Each year. So the number of times interest is applied in a year. So N is the number of times that interest is applied in a given time frame, in a single year. So how many times does he get interest per year? Just once. He's only getting interest one time per year. But because the time frame is 12, he's going to get it 12 times. So there's this subtle difference between N and T. N is typically going to be the number of times that interest kicks in a given year. T is the time frame, how many total years have gone by. Now, if we were to use that fancier formula with all of these values, would we get the same A? Would we get that 3,138? So A equals P, the principal amount. I'll stick to the color scheme here. 1,000 times 1 plus, and now if you look at that formula, it's r divided by n. 0.1 divided by n, but what is n? It's just 1. So is that different than our ab to the x that we originally used to calculate it? No, because we had 1 plus 0.1 in that first time we solved the Spider-Man problem. But because the interest is kicking in only once a year, he's still getting that whole 10% one time a year. Then our exponent is n times t. It's the number of times you're getting that interest per year times the number of years. So that's 1 times 12. Is that going to be different than our ab to the x? No, it's the same thing, right? 1 times 12 is still 12. So this is still just 1,000 times 1 plus 0.1 to the 12th. So if your problem doesn't say anything about like compounding interest daily, monthly, quarterly, or some fraction of a year, then it's going to be the straight up like exponential growth problem that we've been doing. But even if you plug it in to that fancier formula, you're still going to get the same result. So this is like the ultimate end all be all formula for you to know for this exponential growth. All right, I guess a lot of heroes get a discount on their finances this year. Wolverine started an account with $200. And that account earned 6% interest, but that was compounded monthly. So what will that account be worth in 20 years? So this word compounded means like how often the interest is going to kick in. But he's getting this 6% interest not each month. That's per year. He gets a total of 6% interest. But since it compounds each month, he's going to get basically 1/12 of that 6% every month, which is what, 0.5%. So 0.5% in January, another 0.5% in February, and at the end of the 12 months, that'll add up to a total of 6%. So A equals, the principal amount is 200 times 1 plus R. 6% as a decimal is 0.06 divided by N. How many times will this interest kick in over the course of a year if it's compounding monthly? How many months are in a year? 12. So we would have to divide that 6% by 12. And he wants to know how much will it be worth in 20 years. But remember, he's getting this interest not just once a year, but how many times per year? How many times does the interest kick in each year? 12 times, right? So in 20 years, he's getting interest 12 times those 20 years, right? For each month over the course of those 20 years. So you take the number of monthly interest compounds per year times those 20 years. So this is what we type into our calculator. So it's going to look like this. 200, the starting amount, parentheses, 1 plus. Now to make a fraction, we're just going to use a division symbol. So 0.06, that's that 6% that he gets per year. But it's compounding monthly, so I'm dividing it by 12 because he gets 1/12 of that interest each month. The exponent then is going to be those same 12 months a year times 20 years. Because he's getting interest 12 times a year over the course of 20 years. So that total number of months, 240 months, he's going to be getting interest. We should get 662. Anybody else get that in their calculator? Make sure you can type it in to your calculator to get that same result. Because I know a lot of you, there's a bunch of different types of calculators we have. Make sure you can do this and get that same answer, 662.04. 662.04. Is everybody able to calculate this number in their calculator? Or were you able to figure it out? You got it? Everyone good? You couldn't? Okay, so try typing it in. Start on the left. Parentheses. This button right there. Y to the x, that's your exponent. And use parentheses because you want to multiply them. So do a parenthesis 12 times 20. No, do the parenthesis first. 12 times 20, close parenthesis, enter. Uh-oh. So you might have to do 1 plus to the parentheses. Okay, so this number that you got, basically we did the exponent piece first and got this. Like we did the 1 plus 0.06 divided by 12 raised to the 12 times 20. Then just multiply it by the number in front. So like that times 200, do that right now. There you go. So just do the exponent first and then multiply by whatever that starting amount is. Do that last with that calculator, okay? Oh. 0.06. So your exponent, it's only raising it to the 12th, then multiplying by 20 separately. So what you want to do when you do your exponent is do parentheses 12 times 20, close parentheses. See, like put the exponent in parentheses like that. Now hit enter. There you go. So just because order of operations, it thinks, oh, raise it to the 12th, hit enter, then multiply that result by 20. You want to do 12 times 20 first, get that exponent, then raise it to that new exponent. So that's why you want to group it with parentheses on that calculator. You're welcome. Everybody else okay? Everyone else good at home? We're all right? Cool. All right, so when we read these problems, we're going to see these different terms. Again, this is coming back to the warm-up. Whenever it says it's compounded, and it will tell you how often, compounded annually, quarterly, weekly, daily, that's going to tell us essentially what the value of n is in our problem. So if it's compounded annually, what should the value of n be? If it's annually, how many times a year is annually? It's just once, right? So that's going to be 1 time a year. If it's compounded quarterly, what number should n be? Quarter, there's 4 quarters, right? What about weekly? What number would you use if the interest is compounded weekly? Yeah, how many weeks are in a year? 52, right? If interest is compounded daily, what's the value of n? How many days are in a year? 365. So you notice as the time frame gets shorter and shorter, n gets bigger and bigger, right? Like a quarter is, then a week is less than a quarter. A day is more frequent than a week. The numbers get bigger and bigger and bigger. What if the problem says that you're getting interest that's compounding continuously? What number should we put in then? If it's just, it's continuously just getting interest like nonstop. Sideways 8. Infinity? Can you type infinity in on our calculator? You can't, right? So if it's more frequent than every day, right? So the daily means the interest kicks in once at the end of each day. Continuous means, every hour. What about every minute? Or every second? Or every millisecond? Or every nanosecond? I mean, how small can you break it down? Can we give that a number? Not really, right? We can't, no matter how small of a number you give me, I can make that number smaller by dividing it further. So what do? Compound it continuously. Well, it turns out that we have one last formula that we can use only when things are compounded continuously. That's going to use a certain friend that we learned about last week. Remember E? E is the base of a natural log. And as I mentioned before, the reason there are two log buttons in your calculator, there's the common log, which is base 10, because our numbers are a base 10 system. And then there's base E, the natural log. The reason that natural log gets its own special button, its own special way of writing logs, is because it's used whenever interest is compounded continuously, or anything that happens continuously. So like down here, population growth. This actually would be happening continuously, because imagine if I said there's 100,000 people in Milwaukee, and the population then doubles every 5 years. Does that mean that in the year 2000, there's 100,000 people, and there's only 100,000 for those 4 years and 364 days? Then all of a sudden, right at year 5, boom, 100,000 new people just show up like that? Are they all born instantly on the same day at midnight on New Year's? Wouldn't that be insane? Right? The population doesn't just change one time at that 5-year mark. It's continually changing, right? Over the course of 5 years, the population is growing until it is doubled 5 years later. So because it's happening constantly, population growing, throughout pregnancies and people being born nonstop, whatever, then we would use this PERT formula. Same thing with interest. If interest is compounding continuously, it's happening just constantly. It doesn't stop. We use E for the base. And also, we have R times T. So you don't even use N anymore. Remember, N was like the number of times it kicks in per year. But if it's continuous, we don't have a number for that. We can't use infinity. And so then R is the rate as a decimal. That gets moved up into the exponent spot. And then T is still time, how many years go by or whatever. So when you see compounding continuously, we use this formula, which we cleverly call the PERT formula. Does anybody know why we call this the PERT formula? Can you figure that out? I hope so. It's because it reminds me of my favorite shampoo brand, PERT Plus. It's 2-in-1. Shampoo and conditioner for my luscious hair. Oh, I have a little bit left. Now, it says PERT right there, so you think of that. This is frequently called the PERT formula. It's used whenever something's exponentially growing continuously. It's never changing. You can't give a little time frame of, after a year or a day, boom, it changes. And then boom, the whole thing changes again after another day or year or whatever. It's constantly growing throughout that whole time frame. All right, the population of Sokovia is currently 23,000. And it's been growing at a rate of 3.4% each year. How high will that population reach in 20 years? So now we have to use a certain formula. Since populations are constantly growing, we want to use the PERT formula. So if you see like a population or something compounding continuously, you want to think about using PERT. So do we use A? A equals P, just like it was in our earlier formula, that's still just the starting amount. Right? These exponential equations are all the same format. The starting amount would be 23,000 times E. Now, is there a number somewhere in this word problem where I can find E? Is E a variable that I have to look for in the word problem? Nope. E is a number already built into your calculators. It's that special number 2.71828, etc. You don't need to know what number it is, but it is a constant, similar to pi. And that E is raised to the R times T. R is the rate, but again, we never put percentages into our equations. We convert it to a decimal. So I'm going to write this as 0.034. And that's being multiplied times the time, which is 20 years. It's important to note that those two numbers are up in that exponent spot. On your calculator, what you might want to do is to put these in parentheses as well to make sure that your calculator is multiplying those two numbers together first before it raises e to that exponent. I think when you use e, it even does give it a parenthesis by default. So let's take a look. Starting amount, 23,000. That natural log button on the left, ln, but it's the second function of it. See just above it to the left in blue, it says e to the x. So to get the e, you're going to press second ln. And on the screen, it gives you e, and look, it's already moved the cursor up into the exponent spot. Now, if you have a calculator where it actually moves up into the exponent position, just like this one, you don't need to use parentheses around the two. You can, it won't hurt it. But if you just have like a caret or a scientific calculator where it's all putting it on one line, you're going to want to do a parenthesis for that calculation of the 0.034 times 20. So 0.034 times 20. And so you're using E in your calculation. Hit enter. Anyone else get 45,399? Yes. All right, everybody, make sure you can calculate this on your calculator right now. Make sure you can type those in and get that exact same value, because this is something you're going to have to do on your own. What I would suggest doing is do the e to the exponent first, and after you get that, then multiply by 23,000 at the end. Oh, so for this one, I think it's doing it reverse. So it's going to do your exponent. So for this, you use the exponent first. So 0.034 times 20 raised, and that's e to that power. So it's backwards. All right. You do the exponent first, then do the second e to the x, get that, then multiply that by the starting amount of 23,000, and there it is. All right. Thank you. You're welcome. Oh, I'm okay. I'm a ninja. I'm allowed to trip. So for the e to the x, you have to type in the exponent first. So do the 0.0, yeah, do parentheses, the 0.034 times 20. Okay, now second e to the x. Good. So that is what e to that power is. Now multiply by the starting amount. Equals 45399. There it is. You're welcome. Good. Let's check over here. What's the e on this one? See, it's right there, the second function. So to type that, you do like shift. But for these ones, it wants you to type the exponent first and then hit that button. So what we're going to do is do the exponent calculation first. So like parentheses 0.034 times 20. Get that. Then do shift e to the x. It's going to be e raised to that power is this. Then multiply by the starting amount. So times, yep. And that 45399, 45399. So you're just kind of doing the whole thing backwards pretty much. You're good? You figured it out? Good? You got this? All right. Alex, you okay? You got it? All right, one more. Everyone, go ahead and try the next example on your own.
You try doing it like backwards too.
Let me see this. I just did, and it happened. Oh my gosh. No, that'd be worse. Okay, so here's our exponent button. There's natural log, so there's e's up there.
Oh, okay.
See in the orange?
Yeah.
Whatever, so you hit the shift key. So shift this, and that does e to the power.
Okay.
So we can then do the 0.034 times 20. So that's e to the exponent. You can just calculate that first.
And then multiply by that?
Yeah.
Okay.
So go ahead and hit times. 45399.
Perfect.
Got it.
Thank you.
You're welcome. Try example 4. What does Snorlax need a bank account for? What's that? You're changing the names? Yeah. Oh, man. You think it's better to mix Marvel and DC? Yeah. Than to mix Marvel and Pokemon? Yeah. Whew. You're mixing direct competitors. All right, do we try identifying everything and plugging them in? So this one's a little bit different. So let's start with these ones that get a bit more complicated. Let's just identify all the values and all the variables and everything like that first, and then we can plug them into the equation to see what we need to solve for. So A is the final amount. Do we know what the final amount here is going to be? Okay, he wants to know how long would it take to reach 700. So 700 would be the final amount. He wants to get to that point. He wants that much to be in the bank account. P is the starting amount. That's 400. Right? He currently has 400. R is the rate. Just look for the percentage. So that's right here, 5.7. But don't write down 5.7. You want to move the decimal two spots to the left. 0.057. N, the number of times that interest is applied in a year. Since it's compounded quarterly, what should the value of N be? Quarterly means 4. So N is 4. And T is the time, the number of years it would take. Do we know what that number is? No, it's because it's asking how many years. So in this case, T is our unknown. So we're going to have to solve for T. So plug everything else in and solve for the unknown. Just using good old-fashioned algebra. So I'm going to plug all these values in. And we've got 700 equals 400 parentheses 1 plus R divided by N, that interest rate divided by the number of times it kicks in per year. So 0.057 divided by 4. All raised to the n times t. N times, oh wait, we know n, that's 4. So 4t. Hey, where is our variable located in the exponent? So what are we going to have to use to solve this problem? We're going to have to use logarithms, right? That's how we solve for those unknowns in the exponent spot. So let me go back to a single screen here so we can zoom in on the calculation. So now we're bringing back solving those exponential equations from last week. I want to get the variable by itself. So I need just the base, the exponent, and the answer. So I'm going to start by getting rid of this 400. So I want those to cancel out, so I just have a base, an exponent, and an answer. So 700 divided by 400 gives us 1.75 equals, if you want, you can do this calculation in the parentheses, 1 plus 0.057 divided by 4. We get another crazy decimal, 1.01425. By the way, I do suggest that when you do have decimals in the middle of your calculation, like right now, I haven't solved the problem yet, don't round too early in your problem. Because if I did round this right now, and I'm not done doing my calculation, I'm going to get a very different answer at the end. So in the middle of your problem, take more decimal points than you think you need. Go 4 or 5 or 6, just to be safe. And then round at the very, very end. And this is raised to the 4 times t. So at this point, this is just a basic exponential equation that we need to solve. There's an answer, a base, and an exponent. We can rewrite this in log form to get that variable out of the exponent spot. We start by writing the word log. The base goes in the basement, so the subscript is going to be the 1.01425 of the answer of the 1.75, and that equals my exponent of 4t. So I just rewrote that in log form. To calculate log with a base that's not 10 or not e, we use the change of base formula where you actually do like a fraction of 2 logs. So I'm going to rewrite this as the log of 1.75 divided by the log of 1.01425. Remember that the log that was in the base stays in the basement. It stays in that denominator spot. And that's equal to 4t. Well, on the left, we can calculate that. You can calculate a log. So log of 1.75 divided by log of 1.01425 gives me another big decimal of 39.55043. and that equals 4 times t. What's my last step? To get the t by itself, divide by 4, and we see that t equals 9.9, this would be like years. Can you have 0.9 of a year? Could you? Yeah. If it's a time frame, you can have decimals. If this were like a population, though, could you have like 0.9 of a person in a city? Gap. Come on. All right, so this is kind of putting a lot of things together that we've learned over the past 2 weeks, all in one problem. And this right here, this is why we learn about logs. So you can figure out, hey, how much time would I need to save up a certain amount of money or to be able to afford this? Questions on any of these calculations? All right. Evie invested $27,000 in an account that pays 12.2% compounded continuously. How many years will it take for her account to reach 100,000? So how many years? That means we're going to be solving for t. We're going to be solving for the exponent again. But the difference in this problem from the previous one is that this is compounded continuously. So there is no n. There's no number of times per year that the interest kicks in. Since it's compounding continuously, we use the PERT formula. So the final amount, 100,000. The starting amount is 27,000. Man, that Evie is rich. E is just E. It is a number. You just put that number E right there. To the R times T. R is the rate, 11.2%. As a decimal, that's 0.112 times time. And we don't know what time is. We don't know how long it will take. We don't know how many years that will be. Go ahead and try to solve this one on your own. Can you solve this equation for t? Look at the previous one, look at what we did, and try to do those same steps on this problem. It's very, very similar to the example we just did. Give it an honest to goodness effort right now. Don't be afraid to make a mistake. Nice job. Mm-hmm. Yep. Yeah, keep going. You forgot the 27,000, the starting amount. A lot of you are starting off the right way, dividing out that 27,000, right? Divide, divide. So that those cancel. Get something like 3.7037. And then from there, you have a base, an answer, and an exponent. Rewrite it in log form. What would the base of the log be? Like, what's holding up the exponent? So back up here. Yeah, e. So since it's e raised to a power, e is your base. And log base e, we got a button for that. So we just use the natural log for this one. That works. Yep, the change of base. It's the exact same calculation. Remember that log base e is the natural log. So when I rewrite that in log form, log base e of 3.703, instead of writing log base e, we would use the natural log, because that is the log of base e. So it's the natural log of 3.7037 equals 0.112t. So that's something I can just type right into the calculator. ln of 3.7037. Enter. Once you get that, then we just need to get the t by itself. So divide by 0.112, divide by 0.112. So those cancel out to get the time. And did anyone get something like 11.7? Yes? So time equals 11.7 years. Yeah. What's that? Okay, what'd you do? Sure. Using that like change of base formula. Okay, so you wrote log of 3.7037 divided by the log of e like that. Goes to 0.112t. Yeah, so that's the change of base formula. You're 100% allowed to do that. But I would just say try to get to the point where if you see that a log is a base of e, just press ln on your calculator. It's less buttons to press. And it's also showing insight that you make that connection between a log of base e is the natural log. And again, that's kind of why the natural log is a thing. That's why it has its own button on its calculator. It's for solving this PERT equation primarily, because this is used all the time all over the world. This formula, if you want to figure out how much time it's going to take for something that's growing continuously to reach a certain point, they use the natural log to solve this exact equation. This is what real people use, not just in algebra classrooms. Other questions on this? Okay, we've got one more. And I'm seeing some students are just like writing the first line then stopping. If that's all you're doing, then you're not going to be able to learn this. You have to actually keep on moving forward and trying it. And you have to be willing to make mistakes, be willing to mess up and do something wrong. That is the only way you're going to learn this. And you have a test in 2 days. And you're going to be doing this exact thing. So if you don't know how to do it right now and you're just sitting there watching it, it's not going to magically jump into your head overnight. You've got to practice it. You've got to work at it. Here's our last one. Gengar is going to invest $130 and leave it in the account for 19 years. And he needs to know, what should the interest rate be? Like, is he looking at different banks and checking out their interest rates? He's like, all right, what's the best interest rate that I can get to make sure that I can raise that account to $330 in 19 years? What formula do you think we should use? Does it say anything about compounding continuously or quarterly or monthly or annually or anything like that? If it doesn't, you can just assume it to be annual, so just once a year. So we wouldn't have to use PERT for this problem. So we got the final amount. So if we use our just generic exponential growth problem, or that finance one, the rate divided by n, well, n would just be 1 because it's just compounding once a year annually. So it looked like this, just our generic exponential growth. So this one we're solving for r. Had to divide out. I want to take a 19 through. If it was compounded continuously, though, that's actually probably going to be a little bit easier. I kind of wish I changed this problem. Do you want to make it a continuous one instead so it's easier for you? No? All right. Well, you can work it out either way. So I'll be okay if you just do the PERT one. Times e to the r times 19. So we just use a natural log again on this one. Yeah, what's up?
Really? Like that plugging in? Like just like that?
Yeah.
And then
Log base E, that would be ln. Did you use the natural log? So log
for
base
this?
E, yep.
So you do this and then you do log
So it'd be
with this calculator.
this button, ln. Yeah,
Yeah.
so you'd type in that, and then you'd just press ln.
And then when I have to press log too.
So ln is a log with base
Okay.
E. So you could just type in that decimal,
And
then
go out.
ln. Yes, exactly. Yeah, good. All right, I'm seeing some good answers. How do you cancel out that exponent? Yep, but since it's to the 19th, it'd be a 19th root. So there should be a root with an opening. Yeah, so you can do any type of root. So we divide off that initial amount so that we only have a base, an answer, and an exponent. And we're going to get like 2.53846 equals e to the r times 19. The base is e, so that's going to be a natural log. 2.53846. Logs equal exponents. The exponent was r times 19, the rate times the time. So then to get the r by itself, we would just divide by 19. So if you type that in, just ln 2.53846 divided by 19. You get r as 0.049. If I want the rate as a percentage though, what number should I use? Move the decimal 2 spots to the right. So in this case, we would multiply by 100, get about 4.9%. Anyone get something similar to that? Okay. Oh, sure, with the 1 plus the rate? Yep, if you do this the other way, 330 equals 130 times 1 plus r to the 19th, that one. Okay, so just a regular exponential growth. So from here, divide by the 130 still. So that was like 2.53846 equals 1 plus r to the 19th. So our goal is to get the r by itself, but it's trapped inside the parentheses. I want to cancel out the parentheses. So look at that exponent of a 19. To cancel out an exponent, you would take a root, right? If that were squared, we'd take a square root to cancel it. Since it's a 19, we take the 19th root of both sides. On your calculator, if you ever want to do a 19th root or something other than a square root, if you go into the math menu right here, you'll see down option 5 says X root. That's for a different type of root. And so if you hit it, it'll either give you that exponent there, or the index, I mean. You could type in 19 of 2.53846. 1.05 we get. equals 1 plus r. Subtract the 1 from both sides, and you get 0.05 equals r, which is going to be about 5%. Is that pretty close to 4.9%? Yeah, for sure. She'll still get a similar answer. It is a bit different because this way would be if that interest were compounded once a year versus if it were compounded continuously, throughout the year. So it is going to be slightly different. Very small, but still. All right. Now, to make sure we understand these, what could we do? What do you think I could have prepared for you to help you practice, to make sure you understand how to do these? Delta math.